So now we know microscopically what those little electrons are doing in the material. So now we have to go back to the wave equation. How does it affect the wave equation? The electromagnetic wave equation comes from Maxwell's equations. And the simplest way to get it is to assume no charges and no currents, what we call empty space. That simplifies Maxwell's equations, and then we had a little process in the differential form how we get to a wave equation. But now let's say no charges, no currents, but acknowledge we're in a dielectric. So there are charges there. They're just in a neutral material, so they always cover each other up. Or do they? All right, so let's see what will happen. So we're going to look at Maxwell's equations in differential form. So we start with Gauss's law. Del dot E in introductory physics, you'd say it's equal to the charge over epsilon naught. If you're talking about no charges, you say it's equal to 0. But now that we're in a dielectric, you say it's equal to rho bound, the bound charge, over epsilon naught. So what does rho bound mean? Let's see. So rho bound means the charge you get from polarizing the material. Okay, so rho bound, and I want to stress that it is real charge. It's not some fake thing. So one way it's real, we already talked about. If you have a dielectric material and you apply electric field and you polarize it, you push positive charge to the top, which leaves negative charge on the bottom. That's a real surface charge. It can really create fields, and you really have to keep up with it in Maxwell's equations. But it's not just surface charges. You can actually imagine this situation. So let's say you have a dielectric material, and you apply a spatially inhomogeneous field. Okay? So let's say you apply an electric field that gets bigger as you go up. All right. What that's going to do is give you a polarization of the material that gets bigger as you go up. So now imagine a little region of this material. In this little volume, let's see, you're going to push positive charge up and negative charge down, and up here you'd get some positive charge. But what would get pushed into this, or pushed out of this region? Let's see, you would push positive charge out, so you'd leave the top negative like that, and you'd push positive in. But it's actually stronger effect up here than down here, right? Because here we have a larger polarization. So when you have a gradient in the polarization, you can actually get a bulk charge in some volume. Okay? And of course, a bulk charge can also affect the field. So you actually do have to keep up with this. This is real charge. You can think of it as in a neutral material. It's just unveiled charge. It's charge that is made to not be covered up anymore. So we write it like that, or if you really want to get into the field theory, you can write that it's the negative gradient of the polarization, if you want to do it in terms of, completely in terms of the differential form. All right, so being in a dielectric does not create magnetic monopoles. Del dot B is still 0. At the extent we care about, it does not affect Faraday's law. So del cross E is still minus dB dt, so that one stays the same. And Ampere-Maxwell del cross B, we were saying, let's see, we were saying that's mu naught epsilon naught dE dt. This was Maxwell's displacement current that he added. But now you can have a current. We said no currents, but if your bound charge is going to change in time, that's kind of like a bound current. So that would be mu naught dP dt, change in the polarization. So we're not deriving and completely justifying these, but this gives you the idea of what happens to Maxwell's equations in a dielectric material.